Were you all at least able to get up to this far? And you were continuing? Okay, continue. Sweet. How many of you were at least able to get up to this far? Nice. Now let's all simplify the last part, this next ending part together. So right here we have 3 to the 0, which is 1. You have 2 to the 5th, I to the 5th times 1. So that would be, let's not go all the way right here. Let's write this out right now, is 32 I to the 5th. Now actually, before I move on, I want to point something out. One thing you should always do is say to yourself, degree 5 should have 6 terms, 1, 2, 3, 4, 5, 6. And degree 5, before we simplify, should have a 5 everywhere. That just kind of helps reassure me. Okay, continuing now. Now, right here we have 2 to the 4th times 5 times 3. What is that coefficient? Thanks.
You're running my son's team. I got them all yet.
Okay, how many of you were able to get this far? Nice. Okay, let's go through now. One thing to note, before I simplify, I start here. Another thing to make sure you've done it right is it should be degree 5, 4, 3, 2, 1 constant right now. And then because this is a complex number, we know a couple things. We know I squared equals -1, and then I is I. Now, I don't like go through and memorize what everything else is. I just think of these in terms of I squared. So we have 32 I to the 5th. Isn't I to the 5th I squared? I squared I. So that would be -1 times -1 times I. So wouldn't that just be 32i? So we have a 32i plus, now I to the 4th is I squared, -1 times -1. So wouldn't that be plus 240? And then I cubed is I squared times I. So that would be -1 times 720 times I. So -720i. I squared is -1 minus 8, minus 1, 8, I can't speak, can I? Minus 1080, and then plus 8, 10i, plus 245. I need to focus. Plus 243. Okay, sweet. Combine real numbers with real numbers, imaginary with imaginary. So what are your real numbers? 527? -597. Plus 122i. This would be how we would write it correctly, A plus BI format. Any questions? Sweet. That was a fun one. Okay, now I had a valid question last time. People asked me, when would we use the binomial theorem over Pascal's triangle? When Pascal's triangle is so much easier, right? Here's an example of when we would. Sorry, Robert's distracted. So we would not want to use Pascal's triangle here. Why not? Let's pretend I gave you a blank piece of paper and said you have a minute to finish this problem. Now, yeah, you're right. Pascal's triangle going down clear to 20 would take us way too long. Binomial theorem would be more helpful. So everybody look what you would do. You'd say, okay, 1, 2, 3, fourth term. We only care about this one, correct? Now think about it. Since it's degree 20, this would be 20 choose 0, 20 choose 1, 20 choose 2. So this will be 20 choose 3. So that would be the coefficient. Let's do it. 20 factorial divided by 20 minus 3 factorial times 3 factorial, right? So then that's 20 times 19 times 18 times 17 factorial divided by 17 factorial, 3 factorial. 17 factorials divide out. 3 factorial is 3 times 2. Well, look, 18 and 3 becomes 6. 6 and 2 become 3. So now you would calculate it. 20 times 19 times 3. 1140. And now we could continue. So we know that this is 2x to the 20, 2x to the 19, 2x to the 18. So then we're going to have a 2x to the 17. Now let's start back here. Negative 3y to the 0, negative 3y to the 1, negative 3y2, negative 3y squared raised to the third. Wasn't that where I was at? 0, 1, 2, 3. So then our final answer, we're almost done. We would have 1140 times 2 to the 17th times negative 3 to the 3rd, x to the 17th, y to the, raise a power to a power, and you multiply. Very good. Now you would simplify that. Go. Just say the in a row. You got it? Y to the 6th. All right. Do you think we got it done in a minute? Yeah, about. Okay, sweet. That's a big numbers, but this once again would be why this would be useful versus Pascal's triangle. Does everybody see the use? Okay, sweet. Let's get to today's lesson. So today's 3-1. It's arithmetic sequences and series. We're going to start out with arithmetic sequences. You'll want to take some numbers. I really like this lesson because this unit is actually one of the most applicable in real-world situations unit. If you had a hard time with this last year, give it another chance. It usually makes more sense this year to people. They're able to understand it better. So everybody, it's sometimes helpful to represent a situation with a sequence of numbers. Now, there are different types of numerical sequences. Not all of them are arithmetic. Not all of them are geometric. Some are just different than that. So we're going to be dealing with arithmetic sequences. So a sequence of numbers, for example, 1, 2, 3, 4, is just a bunch of numbers in a sequence here. Does everybody see? Now, what makes this an arithmetic sequence is that there's a common difference from one term to the next. So what we're doing is 4 minus 3 is 1, 3 minus 2 is 1, 2 minus 1 is 1. Do you see how it was the same every time? So essentially, we were adding 1 each time. It had a common difference, so this would make it arithmetic. It's changing by the same amount each time. So everybody, look at this one. Is it arithmetic is my question. So 18 minus 13 is? 13 minus 8 is? And 5. So it is arithmetic because we are adding 5 each time. There's a common difference of 5. Now look at this little saying here. See why this saying makes sense here. This is just saying what an arithmetic sequence will look like. Now think about it. If A is our first term, then isn't this going to be our second term? Take the first term and add the difference. Take the first term and add the difference. Like 1 plus 1 is 2. Now think about it. Our third term here would be take the first term and add the difference 2 times. Doesn't that make sense? Add 1 2 times and we're at 3. Does that make sense, everybody? So this is just telling you the format of an arithmetic sequence, which it makes sense. Okay, what I want you to do is 1 through 10. So it's asking you, is this arithmetic? If so, tell me the common difference. If not, just state no. Ready, go. Okay, so now we just got to talk about some notation, because this confuses people. That's the hardest part for people, is understanding what the notation means, because they confuse what it's saying. And it was kind of, people in second hour were kind of doing this. So everybody listen. So a sub 1, literally, no, that's just notation of saying the first term in the sequence. First term. Does everybody understand? Then this would be the second term, third term, fourth term. So let's test your knowledge. If I said find a sub 10, which term am I asking you to find? The 10th term. You're right. Does everybody understand? All right. Now a sub n is just a way of saying any term or the nth term in a sequence. So look, a sub n, couldn't I plug in any number for n? A sub 1, that'd be finding the first term. A sub 2, 3, 4, 5, a sub 100. Wouldn't that just mean the 100th term? So a sub n means the nth term, or you're going to hear me say any term. All right, and then a sub n minus 1. This is not a sub n minus 1, it's a sub n minus 1. So what that literally means is, isn't that 1 less than a sub n? So this does not mean you take the term and subtract 1. What this literally means, in words, is the term before a sub n. So for example, if I called this a sub n minus 1 would be 3. Does everybody understand? A sub n minus 1 literally just means you say it out loud, the previous term, the term that comes before. Everybody good? So a sub n plus 1 just means the term that comes after a sub n. It has nothing to do with adding 1. It just means the next term. So if this is a sub n plus 1 would be 8. Does everybody get it? Okay, so my question, let's test your knowledge. If a sub n is 3, what's a sub n plus 1? 5. What would a sub n minus 1 be? 2. Okay, good. You guys get the notation then. Awesome. All right, now what I want you to do now is, as with yourself, knowing this notation here, I want you to write me a formula. It might be wrong, and that's okay. It's all just trying here. I want you to write me a formula that will generate any term in the sequence for these numbers. Not using notes, just using your brain. Think. A sub n, I want a formula that will give me any term in the sequence. Ready, go. It doesn't have to be super complicated, just think a little. So a lot of you are thinking, that's all I wanted you to do, is think a little bit. So I think a lot of people say, well, we're taking the previous term and adding 1 here. Isn't that true? So good job, group. You're right. And I saw some people in this group. They literally put a sub n minus 1. You take the previous term and you add 1. Isn't that a true statement, everybody? Yep. That's the easiest one to write, which was a great way of thinking. Yeah, absolutely. What about here? You could write a sub n minus 1. You take the previous term and add 5. Does everybody see how that does make sense? Now, the only problem with that formula is if I said to you, okay, great, I do like that formula, and I do. I want you to find a sub 1,000. What are you going to need to know? The term that comes before 1,000. Isn't that going to take you the rest of forever? Because you're going to have to go through clear till you find that term. Does that make sense? We don't know what this term is. We would need to know the 999th term. Does everybody see? Which is not very helpful, correct? So these formulas are great. They're easy to write, but they're not very helpful. So that brings me to my point here. So a recursive definition is what you just did. So everybody in your notes, you should be writing this down. So a recursive definition is the definition that's easy to write. It's very straightforward. It's literally just what you see with your eyeballs. Oh, I'm taking the previous term and adding 2. That is a correct formula. However, like I just said, it's not very useful when I say find the whatever term, because you would have to know the term before it. So it's easy to write, not easy to use, not helpful. So for example, let's look at, a couple things that you need. So we know that to write an explicit definition, you would take the previous term plus the common difference, which is what we just did. So look right here. A sub, number 11. If I was to write a recursive definition for this, Are we taking the previous term and adding 2 each time? Adding 2, adding 2. So look, a sub n minus 1 plus 2 would be the formula. Now here's the thing though, you do have to have an initial condition, because what I'm saying is, take the previous term and add 2. Okay, great, but where are you starting? Does everybody see how I don't know where to start? So you would also have to say for this, and let a sub 1 be 12, because that's where I'm starting. So then you're saying, start at 12 and add 2. That would generate this sequence. Does everybody understand? Now, once again, that's not very helpful because, so that's a formula that's easy to write, but it's not very useful, because if I said to you, like in the instructions from 11, find a sub 43, don't we need the 42nd term? So we're going to have to list out clear till we get to the 42nd term to know the 43rd term. Does everybody see how that is not very useful? So I kind of draw a frowny face. We would not use this explicit formula, or sorry, the recursive formula we would not really use for anything besides writing it. So that brings me to an explicit formula or explicit definition. This is a formula that we use. So I put a little heart because we like it the most. It is harder to write, a little bit harder to write. However, it's more useful because you do not need to know the previous term. So this formula is already on your worksheet. I mean, you know that formula sheet you picked up? It's already written there. So it's written on there, a sub n is equal to a sub 1. Make sure you write a sub 1. You take the initial term, starting here, and then plus n minus 1 times the common difference. So if you need to make yourself a note, a sub 1 is the first term. D is the common difference. All right, so and n is what we're like looking at. So n, like if I said 43, that would be a sub 43. The 43rd term, we'd plug in 43 right here. Does everybody see? And this allows us to find any term in a sequence. So this is a lot more helpful. So let's look at number 11. Instead of writing a recursive definition, which we found out to be not so helpful, let's write an explicit definition. So let's write a formula that will generate any term in this particular sequence. So we'd say a sub n, we're doing a general formula, and then a sub 1 plus n minus 1 times the common difference. Then I'm going to make sense of why this formula actually works, and then you'll understand it better in a second. So let's write our formula. A sub n is equal to, what's a sub 1? So we have 12 plus n minus 1, and then what's the common difference here? 18 minus 16. 16 minus 14, 2, so it's 2. All right, now look, I've already done this. Now we could simplify that. So if I wanted to multiply this in and simplify it, we could. So let's do that just for kicks and giggles. So a sub n is equal to 12 plus 2n minus 2. So a sub n is equal to, let's write it in the prettiest format, 2n plus 10. Yeah, and the reason I practice this is because in the future, if I said to you, write a formula that will give me any term in the sequence, you would want to go to here. Everybody see? But because now I'm asking find a sub 43, we could have just plugged in 43 right here. So everybody see how I just plugged it right in? So I plugged in 43 because that's a sub 43 because we're asked to find the 43rd term. Now let's think about why this makes sense. So we'd be doing 12 plus 42 times 2. Now let's think about why this formula makes sense. Aren't we going to be, this is a sub 1. We want the 42nd, sorry, was it 42? No, 43rd term. Now think about it. We're going to add 2, add 2, add 2. We're going to have to add 2 how many times? Well, let's think about it. So if we start with 12, we're going to be adding 2 42 times. Wouldn't that put me at the 43rd term? If I start at 12, aren't I gonna, and I want to get, that's a sub 1, and I want to get to a sub 43, won't I have to add 2 42 times, sorry. So the formula makes sense. Do you see where it comes from? Starting with 12, we're gonna add 2 42 times. That would put me at the 43rd term. Making sense of the formula is gonna help you memorize it better. Does it all make sense? Okay, sweet. What do we get? 96. So if we were to keep adding 2, finally at the 43rd term, we'd be at 96. Let's do another one. Number 12, it says find the 43rd term. Once again, I really highly recommend writing out just a general formula, just in case in the future I say, give me an explicit formula. You'll have had practice doing that, not just plugging things into it. So we would say, let's write a general formula, a sub n. So a sub 1 plus n minus 1 times the common difference. What is a sub 1? 13.1 plus n minus 1 times the common difference. So how do we find the common difference? This minus this, this minus this, this minus this. Don't we get negative 10? So we're subtracting 10 each time, everybody. So we would have n minus 1 times negative 10. Now, once again, I just am practicing it like this because I might in the future not say find the 43rd term. I might just say write a formula. So it's not bad to practice. A sub n is equal to 13.1 plus negative 10n plus 10. So our simplified explicit formula would be negative 10n plus 23.1. Does everybody see? And now I want to know, find a sub 43. So now we can plug that right in. That's why we love the explicit formula. We can plug it directly in. Negative 10 times 43 plus 23.1. What's the 43rd term in this one? Negative 406.9. Are we quiet because we don't understand what's going on? Or just being quiet? All good? Now, once again, how does this make sense? Think about it. If I was to plug in negative 10, if I was to plug in 43 right here, that would be saying we're going to start with 13.1. We're going to subtract 10 42 times, which makes sense because that would put us at the 43rd term. It's all making sense. Okay, cool. What I want you to do is 11 through 20 go. Attention back up here for just a second. One thing I want you to notice is with these arithmetic sequences, all of our formulas, all of our explicit formulas are coming out linear. Now, why does that make sense? Can anyone tell me why it makes sense? Yeah. So Jonathan says, since it's a linear equation, isn't it just going up by the same amount each time? Yeah, so it's linearly getting larger and larger, right? We're adding the same every time. Does everybody understand? You're right. So if I said to you, the reason I point that out, if I say to you in the future, I might not tell you it's arithmetic. If I say to you, given this explicit formula, is it arithmetic, geometric, or none of the above? What would you say? You say it's arithmetic because it's linear. Does everybody understand? Okay, cool. Continue in that section. Actually, I think most of you are done. Are you done with that section or need more time? Okay, so it says find the missing term of each arithmetic sequence. Notice it told us it was arithmetic. So there's two ways to do this. I'm going to show you both because I think both are very useful for different types of problems. So everybody look. Watch because you're going to pick the way you like most. Okay, so isn't it true? Way number one would be to set up a true statement. We don't know what this value is, so I'm going to call it x. Does everybody see? Now to solve, we need a statement, a true statement. Isn't it true? Since it's arithmetic, there's a common difference. So wouldn't it be true to say this minus this will be the same as this minus this will be the same as this minus this, and so on, right? So you'd say 49 minus x will be equal to if we take x and subtract 23. And now you just have an algebra statement. So we're going to combine our x's, add x. So we have 49 equals 2x minus 23, add 23. So we get 72 is equal to 2x. So x equals 36. So we literally just solved for that. What was missing, we know it's 36. That's way number one. Now this other way is better when we get to more advanced problems. For example, if we were missing two values and then I gave you a value, you couldn't use an x here and here because that's not the same value. So you couldn't call them both x because then you're calling them the same. So this is a better way almost to think through it. Now, a lot of you can just see this, but this is what you're doing algebraically in your head. I don't care how you do it, as long as you can do it right. A lot of people can't see it, though. So let's solve a different way. Now, look, set up a true statement. Isn't it true to say 23 plus something will equal that? Plus that same something will equal that? So look at my statement. 23 plus question mark, that equals 49. Now we can solve for question mark. So we would subtract 23. So we have 2 question mark equals, yeah. And then we would divide by 2. So question mark equals 13. So guys, we were adding 13 each time, adding 13. So we would do 23 plus 13 and get 36. Plus 13, we get 49. Does everybody see 2 different ways of thinking through it? Okay, sweet. Before lunch, you can do it either way. Now, what we just did, because there's a lot of you saying, well, I just think of it. I go, there's the distance of 49 minus 23, and then I'm dividing it over 2. Yeah, same thing that we just did. So I don't care how you think through it. Okay, ready, set, go. Now, I've heard the word arithmetic average for this. You might as well. Now, think about why we were finding an arithmetic average. We did this minus this divided by 2. That's this way. That's what an average is, right? We're finding the arithmetic mean. Arithmetic average. We're finding the arithmetic average. So if I say to you, find the arithmetic average, aren't I just telling you to do this? Same thing. Can you shout out what answer you got right here? You got 94 and then? Hey, does anyone want me to go through how they got that? Okay, couple people. I personally would need to maybe set up an algebraic statement. Isn't it true to say that 100 minus something again equals 82? So there's the statement. 100. Oh, I meant plus. 100 plus question mark equals 82. That's a true statement. Solve for question mark. So you'd subtract 100. So then you have 3 question mark equals negative 18. Divide by 3. So it looks like our question mark that we're subtracting is negative 6. So that means we're subtracting 6 each time. So then 100 minus 6, and that's how they were able to get that. Does that make sense? Make more sense? For some people, okay. Sweet. That's exactly what you did. It's just you did it in your head, a lot of you. Okay, cool. All right, we do not need to go through this one, but this is an example of like a real world problem, so make sure you do that one right. All right, let's get to series now. This is where it gets fun. So, we just were dealing with arithmetic sequences. A sequence is just a sequence of numbers. So look, 6, 9, 12, 15, 18. Sequences are separated by commas. A series is separated by addition signs. So a series is finding the sum of those numbers, do you see? And so this is a finite sequence. A finite means you know the start and end. So this would be a finite series. You know the start and end. All right, now infinite sequence, it's a sequence because it has commas. It's infinite because ... means it continues on forever. So we're going to have this continuing on forever. Here's an infinite series. So look, it's 3, 7, 11 plus 15 plus, we're going to be adding forever. Now think about it, guys. Since we don't know the end here and it's arithmetic, isn't this just getting larger by, it's getting larger and larger, right? Everybody by 4 each time? Are we ever going to know when to stop adding? No, we're going to be old grandmas and grandpas still adding because we can add forever, can't we? So we can't find the sum here. If it's arithmetic and it's infinite, we can't find the sum because we would not know when to stop adding. We'd be adding forever. However, if it's finite and arithmetic, we can find the sum because we know where to start adding and when to stop adding. Does that make sense, everybody? A formula for a finite arithmetic series is on your worksheet already. So here it is. S of n means the sum of n number of terms equals n divided by 2 times a sub 1 plus a sub n. So just write this down. N is the number of terms you're summing up. Now in this formula, a sub 1 means the first term you're adding up in the series, and a sub n is the last term you're adding up in the series. All right, so let's look at number 1. You're in on that next page, on the second page of the worksheet, basically, the front of the second page. Are we all good? So it says, find the sum. It's arithmetic because there's a common difference. 9 minus 7 is 2. 7 minus 5 is 2, right? So it's arithmetic and it's finite. We know this where to start and stop adding. Now, obviously, I'm starting out with an easy example to make a point. Obviously, it'd be just as easy to take your calculator and go 1 plus 3 plus 5 plus 7 plus 9, right? I'm just trying to show you how this works because they will not all be this straightforward. So isn't this a sub 1? A sub 2, a sub 3, a sub 4, this is a sub 5. How many terms then are we summing up? So we're summing up 5 terms. I'm plugging it into the formula. That's going to be equal to 5 divided by 2 times a sub 1, which means the first term, plus the last term, and boom, there's your sum. So calculate the sum of those 5 terms. 25. Does everybody see? Now that one was easy because we were able to see the start and end, and it was easy to count how many terms we had. However, you're not always going to be able to see right off how many terms you have. For example, look at number 2. A sub 1 is 5, a sub 2, a sub 3, plus dot, dot, dot. We don't know what this is, a sub n. Maybe it's a sub 10, maybe it's a sub 5. Does everybody see how we don't know? But we need to know because we need to know how many terms we're summing up. It would not be smart to list out all of them and say, oh, I'm adding 3, so I'll just write it all out and then I'll count them up. Because it's going to be impossible once we get to larger things. Like if this was so big, you wouldn't want to list them all out, would you? Like 100 terms you wouldn't want to list out. So the first thing we would have to do is say, we don't know how many terms this is. We need to find n so that we know how many terms this is. So let's first, before we can go plug it in this formula, let's find n. So we're going to use our explicit formula, plug everything in that we know to find n. So a sub n is 26 because we know that that's the term we're trying to figure out. What term is that? A sub 1 is 5 plus n is what we're trying to find minus 1 times the common difference, which is 3. Now just solve for n. Do you see how now I can just solve for n? So then we would subtract 5. 21 is equal to n minus 1 times 3. What would I do next? Divide by 3. So 7 is equal to n minus 1. So then n equals 8. So this was actually a sub 8. So now we know we're summing up 8 terms. So now we can plug it into the formula. The sum of those 8 terms is equal to 8 divided by 2 times a sub 1. First term we were adding up plus a sub n. The last term. And now you would calculate it. The sum of those 8 terms comes out to be what? 124. Does that make sense, everybody? Let's do one more similar. Okay, let's do number 3. Now, once again here, this one is find the sum. We know this is a sub 1. This is the first term. And this is a sub n. We don't know how many terms we're going to be summing up because we don't know how many is in between here. Do it with algebra. So we would say, okay, we do know the formula, an explicit formula for arithmetic. Once again, it's arithmetic because that minus that is 5, that minus that is 5, and so on. So a sub n is our explicit formula, a sub 1 plus n minus 1 times d. Let's put in everything we know. We know our last term that we're looking for is 44. Is equal to a sub 1, which is 4, plus n minus 1 times by the common difference of 5. We're trying to solve for n, because then we can plug it into our formula. So we'd subtract 4. 40 is equal to n minus 1 times 5. We would divide both sides by 5. 8 is equal to n minus 1. So n equals 9. That was the 9th term. And I found that using algebra. So this is a sub 9. Now we can use our formula. S of 9 is equal to 9 divided by 2 times a sub 1 plus a sub n. So the sum of those 9 terms comes out to be 216. Now think of how this could be applied in a real world situation. Let's say I am a mother and I'm trying to bribe my children to help me at home. And I'm not very smart at math or whatever, I'm just whatever at home, and I'm just not really thinking. And I say to my kid, okay, Johnny, if you help me today for chores, I'll give you $4. And then every day after that, I'll give you $5 additional dollars. Isn't that what's happening here? So the first day Johnny makes 4, the next day 9, 14. Well, now Johnny goes off and says, and I say, I'm going to do this for 9 days, Johnny, because I need help for 9 days. So then Johnny goes off to the side and does this summation and says, ooh, I'm going to have $216 by the time Mom is done with chores, having me help with chores. Does everybody see how that would be like applied in the real world? Okay, sweet. Ready? I don't think you need another example, do you? With this, you guys are good. Want another one? All good? Okay, I want you to work on then this section, 5 through 7. So you should really be doing 1 through 7 in that section. So understand what we're doing now is not learning anything new. We're taking and instead of writing it out like this, we're putting it the same thing but in different notation. It's called summation notation. So it says right here, you can use Greek capital letter sigma to indicate that you're taking a sum. So guys, this little sigma sign literally means find the sum. Like that's what those addition signs are, right? And then it says, then with it, you will use limits to indicate how many terms you are adding up. Limits are the least values in the series and, okay, wait, whoa. I cannot read this tilted sideways, sorry. With it, you'll use limits to indicate how many terms you are adding up. Let's just keep this basic here. Now we're gonna write an equation based on our series that we're dealing with. So our lower limit is here, our upper limit is here. So we're always gonna choose to write from 1 to the number of terms we're summing up. So let's say we were summing up 10 terms, and we would write n equals 1 to 10. Does that make sense, everybody? Now we're gonna then also right here is your explicit formula. The explicit formula that generates the sequence or series. So for arithmetic, we know it's a sub 1 plus n minus 1 times the common difference. That's the explicit formula we're gonna put right here. That's what will generate any term in the sequence. However, if you're going backwards, so writing the formula, we're always going to call a sub 1, so we're going to say n equals 1, and then we'll write an appropriate formula. So we'll always be able to go from 1 to however many terms we're summing up. But it won't always be that way if you're going backwards. So for example, look at this example. I don't love it because it's not linear, but it gets across the point. So everybody look. Do you see how this is a 3 right here, everybody? 3 squared, 4 squared, 5 squared, and so on, and then 100 squared. Now look what they did. So they said n squared is the equation. So n must be what right here? If n squared is the equation, then we're plugging in a 3. Does everybody see? So then on the bottom, they said we first started by, what was the first thing we plugged in? A 3. Do you see how they did not start at 1? They plugged in a 3 to begin with. That's still our first term we're going to be summing up in the sequence, though. And then a sub n would be the final term. So look, they plugged in 3 up to 108 into the formula. Does everybody see? They plugged in 3 up to 108 into the formula. So how many terms were they summing up? Well, you can find this, if you think about it. We plugged in 3, got something. Plug in 4, plug in 5, plug in 6, so on, clear till we got up to 108. So how can we find the number of terms we're summing up here? You would do the top minus the bottom, so 108. Minus 3, which is 105, but that doesn't include, so that's how much distance is between those two, but that doesn't include n equals 3, plugging in n equals 3, so you have to add 1. So that's 106 terms we're summing up. So let me give you a more basic example for those that need to see it more in a basic example. If I said the sum of n equals 2 to 8, for example, 2n, how many terms would we be summing up? 8 minus 2 is 6 plus 1 is 7. Now why? Why is it 7? Let me show you. What we're doing here is we can literally rewrite this just as a sequence. So if we plug in 2, we would get the first term, we'd get 4. Plug in a 3, we get 6. Plug in 4, we get 8. Does everybody see what I'm doing? I started with 2 and plugged it in. Plugged in 3, 4, 5. Wait, 2, 3, 4. Plug in 5, we get 10. Does everybody see? Plug in, and then aren't we adding 2 each time? Okay, so 12, and then 14, and then plug in 8, we get 16. Count how many terms if we were to find the sum. How many terms is it? 1, 2, 3, 4, 5, 6, 7. Does everybody understand why we're summing up 7 terms? Okay, cool. All right, and then once again, we just write in our explicit formula for arithmetic. So if I said to you, find the sum, it's not that we're finding the sum, we're just rewriting it in different notation. This literally means the same thing as this. All right, let me get that to this. Wow, this pen. This means the same thing as this. Just different ways of writing it. Do you all understand? Okay, now if I said n equals 1 to infinity, that would be an infinite series. If it was arithmetic, 2x minus 1, for example, could you find the sum? No, you can't find the sum. We would not know when to stop adding. Okay, awesome. Let's do this example, number 8. It says, instead of writing it out, write the arithmetic series instead in summation notation. So the sum sign is taking care of those addition signs. The sum means addition sign. And then how many terms are we summing up? 1, 2, 3, 4. Now we're going to say from 1 to 4. Everybody see? And then we would write in our explicit formula, which for arithmetic is a sub 1 plus n minus 1 times the common difference. So we would have 4 plus n minus 1 times, what are we subtracting? Yeah, we're adding 4. Sorry, what's the common difference? It's 4. So then times 4, and then in our final answer, they would simplify that formula. So we would say from 1 to 4, we'd multiply 4 in. So we'd have 4 plus 4n minus 4. So the simplified formula would be 4n. So once again, guys, it's not that we've done anything. Instead of writing it all out, we're putting it in summation notation. They mean the same thing. Questions? Now, a lot of people say, well, why do we always start with 1? Because we chose to call this a sub 1. So our formula will match up with what we chose to be the first thing. Does that kind of make sense? Okay, cool. Let's do another one. Okay, looking at this one, you'd say, okay, I've got to write this in summation notation. There's addition signs, so that's why I draw my sum sign. From 1 to, well, how many terms are we summing up here? Uh-oh, we're at that place where we don't know. So don't we need to do algebra like in the beginning of the lesson? So we don't know. We know this is a sub n, but we need to know if this is a sub 8, then that'd be 8 terms. If it's a sub 10, it's 10 terms. So let's figure out what term that is. So use your explicit formula. Here we go. So a sub n is negative 5. That's equal to a sub 1 plus n minus 1 times by the common difference. 3. Oh, we're subtracting 3, aren't we? So times negative 3. Now we got to solve for n. So we're going to subtract 10. Negative 15 equals n minus 1 times negative 3. So we divide by negative 3. We get 5 is equal to n minus 1. So n equals, so this was a sub 6. Now we know. Okay, cool. So we're going from 1 to 6. We're summing up 6 terms. Now we've got to write in our explicit formula. It's arithmetic. The explicit formula for arithmetic is a sub 1 plus n minus 1 times by the common difference. And then they would simplify the answer. So we would say n is equal to 1 up to 6. Multiply n negative 3. So we'd have 10 plus negative 3n plus 3. So then reorder it in the linear format. Negative 3n plus 13. How do I know if my answer is right? Because I could plug in 1, see if I get 10. Plug in 2, see if I get 7. Plug in 3, see if I get 4. Plug in 6 and see if I get negative 5. Do you see what I'm saying? Okay, cool. Just different formats. Same exact thing. They mean the same thing. It's just written differently. Okay, I'm going to have you practice a few like that. Ready, go. Do these ones. Remember, in 14, this says find the sum. So because this does not specify that you can use your calculator, you would need to do it by hand. So first of all, we know technically, just so everybody's aware, isn't this the same thing as, okay, plug in a 1, correct? 1 minus 1 is, that's our first term. Plug in a 2, 1, I should put plus signs because that's what the sum means by definition. And then what, plug in a 3, we get, plug in a 4, 3. Aren't I done? Now let's do this not this way, but you guys understand that that is the exact same thing as that. It's just how do you want to write it? Does everybody understand? So now what we would have done, let's just use we know the sum for an arithmetic series is this formula. Now what are we going to have to know? We're going to have to know how many terms we're summing up. So what's n in this one? 4. So you would do 4 minus 1 plus 1, that's 4. What's a sub 1? Plug in 1 is 0. Well, a sub n is the last thing, so wouldn't that be plugging in a 4, which is 3. So now we can plug it into our formula. So we'd say a sub 4, the sum of 4 terms is equal to 4 over 2. We found these things times a sub 1 plus a sub n. So the sum of these 4 terms is 6. The sum is 6, everybody. That makes sense. Why did I write it out like this? Just to show you that they're equal. We're not going to always do that or it defeats the purpose of having this. Everybody good? Okay, let's do another one. Look at number 15. Okay, let's just plug it directly in. We know this is a sequence of numbers, a series being added up, but we're not going to go through and list it all out because that's why we don't want to have to do extra work. We do need to know n. How many terms are we summing up here? 6 minus, no, don't say 6, you're being the statistic. We didn't start at 1, did we? We started at 2. We plugged in 2, we got something. We plugged in 3, 4, 5, 6. How many terms? 5. Let's just use algebra to get it. 6 minus 2 is 4, plus 1 is 5. So we're going to be summing up 5 terms. What's a sub 1, everybody? Well, to know, that means the first term you're summing up, you need to plug in your lower limit, because that would be the first thing we'd plug in. 4 minus 1 is 3. Then a sub n means the last term you'd be summing up. Well, plugging in 6 would be the last thing we're plugging in. So 12 minus 1 is 11. And now we can plug it into our formula. So s of 5 is equal to 5 divided by 2 times a sub 1 plus a sub n. So the sum of those 5 terms is 35. You still got to use the sum formula. They mean the same thing. Yeah, but let me pause. Does anybody have any questions on this one? Okay. All right. Now you finished the worksheet. Now, the only time you'd be able to use a calculator is, notice it says on 23 through 28, it says use a graphing calculator. If you know how to do that, then you can actually just find this. You can type it right into your calculator. But only if the instructions tell you to do that. If you don't, you can do it by hand, and I can show you how to do that. We're going to do that next time on the board. The rest of the time is yours to finish up as much as you can in class.